let's move swiftly on to Zhang from NTU-CTP Institute.
Okay, so thank you so much for the invitation to this very nice workshop. So I apologize today I'm not talking about something directly related to string theory, but I'm going to talk about some kind of mathematical methods, the algebraic geometry method widely used in the computational string theory. But now I just borrow this kind of computation in the study of the scattering amplitudes in quantum field theory. So this talk is based on the work with my collaborators in CERN and also in the Grobner Institute.
Use mouse.
So here is the outline of my talk today. So the physics object I'm going to talk about is scattering amplitudes in field theory. Okay, so it's a high loop amplitude, 2 loop, 3 loop, 4 loop amplitudes. So mainly I focus on the non-supersymmetric amplitudes because it's something related to the real world, and also this method is very useful for the calculation of very hard non-supersymmetric amplitudes. So now, if you traditionally in the Feynman diagram calculate non-supersymmetric amplitudes in field theory, it's quite difficult. The reason is there are too many diagrams, and each diagram is a huge tensor, and sum over all the diagrams to get your answer. Okay, it's a tedious and hard process. So people try to use unitarity method. Unitarity means somehow if you have one loop diagram, if you have double cut, then by the optical theorem. So this one loop diagram can be factorized into a copy of the 2 tree amplitudes. So that method is very successful for the one loop calculation, but for higher loop, so previously there's no systematic way to do the unitarity. So I try to convince you that to do the unitarity method systematically for higher loop, the ordinary methods like optical theorem based on the one variable complex analysis is not enough. Okay, you can not just calculate this kind of residual branch cut of one variable. So instead, you need some new mathematical tools, algebraic geometry. The reason is for unitarity one loop, you don't have so many variables. And for unitarity for high loops, there are so many variables. So complex analysis is not enough. You need the algebraic geometry method. So there are many different ways to do unitarity in high loop from the recent works. So because I only have 30 minutes, so I just focus on one efficient method called integrand reduction. So this method, so first I give you a review what is the integrand reduction at one loop, and then I'm going to talk about the integrand reduction at a high loop based on algebraic geometry. And finally, I give you some physics examples, some new results about the 3 loop random QCP diagram and the 2 loop final point random QCP diagram like this. Okay, so first I review the one loop unitarity a little bit. So from the well-known result from the textbook, you know, suppose you consider the 4D QFT, then for any kind of a renormalizable theory, the amplitude can be written as the sum of the box, a triangle and a bubble, and maybe in rational terms like that. So this statement is non-trivial. It's non-trivial because if you start from the Feynman diagrams, okay, then of course you could have hexagon diagrams, if you 6 glue interacting together in one loop. Okay, but finally you can reduce all this kind of higher topology diagram into the lower topology diagrams. Okay, and also if you start from the Feynman rules, then of course the numerator, if you're doing gate theory, the numerator must be a huge tensor. But in one loop, there's an advantage by unitarity method. You can reduce all this kind of integral to scalar integral. Scalar means the numerator is just 1 here, so it's quite easy to calculate. So in the one loop scheme, unitarity is try to determine this kind of coefficient. This C is just some constant. This box is actually the numerator is 1, the denominator is 4. This Feynman propagates is a one loop integral here. This is a mathematical object calculated non-local by mathematicians. This way, the physics object is a coefficient coming from the theory, coming from the vertex, coming from the kinematics. So unitarity tell you that you don't need to start from Feynman rules to get this kind of C coefficients. Instead, you can determine the C coefficients from the unshared point solutions and also the tree amplitudes. So suppose like the first one, if you cut 4 times, drop cut, then you can convert the loop amplitude into the product of 4 trees, and then you can determine this C box. then recursively you can get C triangle and C bubble like this. And because the value of this integral are already well known a long time ago, so you can get everything just from the tree amplitudes. You never need to do this kind of field theory one loop amplitude by yourself. Then I just go a little bit detail. Sorry.
Question. So how do we previous slide please?
Oh, sorry. Yes.
So how do we know that when we from some pentagon, hexagon?
Yes, I
have
expanded.
And so how do we know how many lines on each vertex?
Okay. So here is a topological diagram. Okay. So this number of the lines, extra lines, equals the number of the external particles. Depends on how many particles in this process. But somehow if you have like a hexagon, suppose you have a hexagon diagram of 6 gluons, but finally you can reduce that into some box like okay, suppose 2 vertices with 3 is another is 2 or something like this. But each vertex attached to several different gluons like that.
So you have to sum over all.
Yeah, you have to sum over all of this. Yes. Okay, so just give a little bit. So how do you get this kind of reduction from the primary roots? So this one is called the Integrand level reduction. The basic idea is still unitarity, but this unitarity, okay, in an algebraic way. It's called the OPP method. So just reduce all this kind of tensor in the numerator by the algebraic method. So from the finite root in the beginning, okay, suppose we have 4 brackets here, and suppose in the beginning you have a tensor nk. K is a local momentum. And the goal is try to decompose this nk as a tensor into several different parts. The first one has nothing to do with the denominator. The second one has 1 power of the denominator. And the third one has 2 power of denominators. So the first one will give you a box coefficient, but this one contains 1d here, will cancel here a d. So this one gives you the triangle, this one gives a bubble like this. Then in practice, the question is how to get this kind of separation. It's quite easy for one loop. Because for one loop, suppose you consider 4D, then this K can contain only 4 components. Okay, you can use the space-time basis like P1, P2, and P3, like not use P4, but P4 is linearly dependent. So instead you design this kind of auxiliary direction omega is perpendicular to all the P's. Then we've written all the components in K as 4 scalar products. You can find that the first 3 are actually reducible. So these 3 are somehow the linear combination of the D's. So by this scheme, they are all reduced. But the last one is not reducible. So although in the beginning this one could be a huge tensor from the finite roots, but finally it's reduced to 1 variable constant like this. So this one contains on 1 variable, but the power is not determined yet. So just one step more, you can determine the power of this constants. You find that suppose you're talking about a renormalizable field theory, the power cannot be very high. So this one cannot be higher than 4, of course. And also, from the Kant equation for this irreducible scalar products, you can find that actually, if you expand this equation, k squared equals d1. d1 is one of the final predicate. So from this equation, you can find that actually, although k to the omega itself is irreducible, but k to the omega 2 squared actually is reducible. So this one can be rewritten as some constant plus other denominators. So just by this kind of decomposition, you get the Integrand basis, which is the constant term plus a linear term. Okay. It's almost the reduction. So that's a reduction in the Integrand level. So here we just use the combination of the denominators, algebraic linear combination several times. Then you get this kind of separation. That's one step further. This is an integral reduction. So you say this constant term will give you the 1 in the numerator. This is the master integral. This one is a tensor integral, but by symmetry, the integration over this one is 0. So this one is spurious term. So you get only 1 in the numerator left. So it's Integrand reduction. And furthermore, if you know this Integrand for a box, then you can one step more, you can get the triangle contribution and also bubble contribution. And if you d-dimensional rational term contribution. So the point is, although this term, this previous term is after integration is 0, but somehow keep it for a while, because for the integrand level, it's in the integrand. You have to subtract that, and then you can do this kind of integrand fitting again for the triangle. Okay, so the intermediate step, and then I can do this kind of bubble thing, just one by one. So everything in one loop is straightforward. You can do box and do triangle, bubble, and also d-dimensional box, and everything like this. You can determine for each one how many scalar products are there, and also the number of terms in the integrand, and also the number of solutions. So, for example, for this one, you say, if you really solve the unitarity solution, you put this form denominator to 0, you find two solutions. In the integrand, there are two undetermined coefficients. So just by linear equations, you can determine that. You can get everything from the tree amplitudes. So everything from one loop, this integrand reduction is automatic. So there are a lot of packages on it. You don't need to think of the detail how to do the reduction, but just tell the program, okay, the kinematics and also the vertices, and just from the tree amplitudes, the program will give you the result for the one loop amplitude. So for one loop amplitude, in field theory, everything is automatic. You can say it's also, okay, no matter what the dimension, no matter how many particles are there, it's straightforward. So because for one loop, this method is very successful. The question is, can you generalize that into two loop and high loops? Okay, because usually, suppose you have some kind of scattering process. Suppose the tree level is not 0, then it's a leading order. If you calculate this kind of one loop contribution, it's the next leading order. But somehow for LHC physics, for many processes, this leading order or next leading order is not enough. We need the next leading order, so we need two loop, even sometimes three loop diagrams. So it's complicated. Then the question is how to generalize that into high order diagrams. Okay, so I just give you a simplest example. You can say this is a two-loop diagram. Okay, suppose we do massless case. You can see that 1, 2, 3 for all belongs is QCD amplitude. So it seems that you can directly mimic the process of integrand reduction at one loop. So you can say here you can find 8 scalar products inside of 4, and you can find 4 calculations left. So STR defines the omega vector, and just like the one loop case, for this squared term in omega, k dot omega, q dot omega, or k dot omega times q dot omega is across the term. So all the quadratic terms in omega, they are reducible. So then, okay, you can find the answers with 4 variables. It's more complicated than one loop. Still is durable, just 4 variables. And you can determine the power, the maximum power from here, coefficients, and you can determine some power from the power continuum of the renowned light theory. Seems that everything is straightforward if you try to generalize the integrand reduction unitarity for two. However, if you do this, the result is wrong. Okay. The result is wrong is in this kinematics. If you make an ansatz like this, you will find that's a very big basis that contains 56 terms in the integrand level. Then if you try to use unitarity to fit all these 56 numbers, you find that you don't have enough number of equations. Okay, that's a big problem. So this counting still is quite redundant. Still there's something remaining. Okay, we didn't consider carefully in this two-loop case some constraints. So where is the constraint coming from? To show example. Okay, suppose you put this m equals 2, a equals 2, and this alpha equals 0, beta equals 0, then everything is legal. Okay, all the conditions, constraints satisfied, but still this term is reducible. The reason is in this case have 3 remaining coefficients for its omega terms. So you can make a nonlinear combination of this. Okay. Just by this nonlinear combination, you eliminate all this kind of k dot omega, q dot omega terms. So what's left is this 2 term is reduced to the lower order terms. So these terms are also reducible. Okay. But for one loop, you never have this kind of problem. For one loop, everything is trivial. You don't have so many equations. Okay. And and you don't need to nonlinearly eliminate some variables. So this is a new issue in the two loop of crossing in three loop, like that. So at that time, we try to exhaust all these combinations for the integrand. And finally, we guess that it may contain 32 terms after try to eliminate all these kind of variables from different nonlinear combination of equations. But of course, it's a tedious process, and mathematically it's not rigorous. Okay. And on the other hand, we have to find a unitarity solution. It's more complicated than one loop. So for two loop, for this kinematics have 6 solutions, and you should somehow connect the equations from each diagonal and find 38 equations. And this linear system, only 32 equations are linearly independent, so you can determine all the 32 terms in the integrand. So this one is done, but it's not done in the mathematical rigorous way. So we try to borrow some new concepts of mathematics. Okay, you see, right now we have several complex variables and have so many equations. So you know, every equation is algebraic, so the ideal tool to deal with that is algebraic geometry. Okay, here we said that we nonlinearly combine different algebraic equations together, but somehow in the sense of commutative algebra, that's called the idea of the idea generated by several polynomials. And this OPP integrand reduction, okay, tells me that we separate this numerator into 2 parts. One is some part in the sometimes some term is proportional to one of the denominators. That just means this term is somehow in this idea. And the remainder term should be the integrand basis. Then the question is, how do you get this kind of integrand basis mathematically? So you know this idea is contains an infinite number of polynomials inside that. So it's not so easy I can get the back separation just by hand. But mathematician has a very efficient way to do this. So this one is called the Grobner basis and polynomial division. Actually, from this generators of the idea, you can find a different general set. This is a good general set. And the mathematician proved that you can do the Euclidean division over this Grobner basis generating set. And after doing this, you get a separation like this. So the first key terms are all reducible. The final one is irreducible. So by this way, you never need to worry about what's the meaning of reducible term or irreducible terms. You just write down this kind of idea and just find the global basis, do the division. Then just in one step, you get the integrand reduction. Okay. So just one step further. Still on this diagram, so this time we try to do it in a mathematical way. We just write down this kind of 7 denominators and think them as algebraic equations. And then from the, you can easily design a package for the just call mathematical to calculate the global basis of the system, and then start from any kind of arbitrary numerator divided by the global basis. You can find this remainder term, which is the integrand basis. You can check that. It really contains 32 terms, and it's an automatic process. And just from the commutative algebra, you can prove that this is the minimum number to have for integrand basis after reduction. So this is my package. So the final thing is somehow I said that if you really try to solve this kind of category system, okay, there are 6 different branches of solutions. It's quite complicated, but mathematically it's something called primary decomposition. So that is, you try to solve a set of the algebraic equations. And the question is how many individual, okay, independent components do you have? So this one can be done in the algebraic way. So there's an algebraic software, the Macaulay 2. It's just starting from any kind of algebraic equation sets. So the software can decompose that into the irreducible, okay, smaller equation sets, and you can find all the independent solutions. So this one has been used for string theories for a long time. If you have some kind of superpotential, you try to find stationary points, stationary branches. So you always primarily decompose this equation system and solve each component one by one. And in this way, you can, of course, we borrow it from the simple system for our unitarity system can find all these kind of color solutions automatically. So combine all this kind of algebraic geometry tools together, we can easily extend this one-loop unitarity integrand method for n loops. So just remember for one loop we have this kind of table. Each diagram, each dimension has a list of the number of scalar products and the number of the integrand terms, the number of solutions like this. Okay. So somehow you see this my package and also this primary decomposition program, you can find all the similar numbers for 2 loops or even 3 loops. So I just give you one 3 loop example, which is this one. So this one is quite hard calculation. You have four massless particles. This you consider an arbitrary Yaml series with nf number of adjoint fermions and nx adjoint scalars. So for some integer value of n, we get this non-supersymmetric theory and supersymmetric theories. So we can just use group basis method to find this integrand basis, and then can use this primary decomposition to find the number of solutions like that. So I will say, okay, after doing this, all the diagrams are separated into the product of the trees. So all the calculation can be done in mathematics for about 20 minutes, and then the final result. And you can say that if you consider X4 theory, then most of the term will drop out, only one scalar term left. But if you consider n equals 0 QCD, then most of the terms survive that. So it's a very complicated result. And for the n equals 0 result, this expression is new. I show another example. It's also a new result which is calculated. So it's a 2 loop 5 point QCD.
Sorry, the previous result was just one.
Just one diagram.
Just one diagram, right?
Yeah.
It's still other
Yeah, it's just to show the power of the method. So this one is really this amplitude. So 2 loop 4 point QCD has been calculated about 10 years ago. But we extend that to 5 point QCD. So the kinematics is much more complicated. Okay. So in this case, we do a d-dimensional calculation, but we still do the integrand reduction. We cut all these kind of diagrams into trees and calculate this integrand coefficients. So here, just the one diagram I show you. So the expression can be optimized into a very simple form like this. We have several diagrams. Okay. So we just calculate the one configuration with the all plus extra legs like this. So there are only 8 topologies, and there are 2 classes of them. So for the all plus amplitude, these 4 diagrams results are very simple because they all proportional to corresponding X4 result. X4 result is called the scale result in this case. But there are also some diagrams. Okay, here there's no corresponding X4 diagrams, so the results for these diagrams are quite complicated. But anyway, we just use the unitarity method. Just from the products of the tree amplitudes, we can reconstruct all these kind of results. And the similar process should work for the long-term diagrams, and is under progress by our group. So just off topic a little bit, I tell you how to get this kind of NTU result. Okay, just from this unitarity cut calculation. You can use something called the momentum twist parametrization method. So previously, when people calculate the helicity amplitude, they always use spinor helicity formalism. So basically, you can write all these kind of long vectors as left moving, right moving wheel spinors, and do everything in the wheel spinor products like this. So this one is very convenient. But the one disadvantage is if you do this, you have to consider momentum condition. Okay, so you can ask the computer to do a calculation, but the result is not so neat. You have to apply this condition to remove a lot of redundant terms and try to get a simple result finally. So somehow we changed our method. We are using momentum twist parametrization. So this one can think that is a half Fourier transformation of the spinor formalism. So by doing this, this momentum conservation is automatically resolved. Okay, automatically resolved. So you can directly do all the calculation for the momentum twist variables. And the result, you can just ask mathematics, simplify everything, and you get the result. It's, everything is automatic. And of course, if you want the traditional spinor form, you can just convert everything back into spinor. That's the way we did for this analytic 5-point QCD amplitude. But of course, if you just want the numerical value for that, then it doesn't matter what kind of formalism you are using. They're all the same. Okay. I just come to my conclusion of this short talk. So basically, the point is the unitarity method is very successful for the one loop scattering amplitude calculation. But somehow unitarity method becomes very complicated, and you need some new mathematical method to treat this kind of unitarity for 2 and 3 loops. So it's just like if you try to generalize this one variable complex analysis to n variable complex analysis, the trivial generalization doesn't work. The trivial generalization of the integrand reduction from 1 loop to 2 loop doesn't work. So we use the new mathematical 2 algebraic geometry to think of this question. We find that by this new mathematical 2, everything is straightforward. Okay, now all well-defined question in mathematics, and there are a lot of package programs to do this. Okay, so we use Grobner basis method to do integrand basis reduction for 2 and 3 loops, and we use the primary decomposition method to get the global unitarity structure. And this work, well, it's just some first step towards the automatic high loop amplitude calculation, because right now we are using several different programs in mathematics, my colleague too, form, all these kind of things. Sometimes we use some very formal algebraic geometry calculation. Sometimes we use some kind of physical vertices calculation. So the goal is in future to find one package to do everything together, combined in one package, just like people did for one loop. And I think this method should be very promising for the electricity physics for the next analytic contribution of the 2 to 3 or 2 to 4 processes. Okay, so thanks.
Any quick question for Zhang?
So when you say momentum cluster computation, do you only consider planar sector?
Actually, I think it doesn't matter it's planar or non-planar, because there's just a parametrization, so you have this kind of kinematics. Then the question is just how you resolve this energy momentum conservation, but this has nothing to do with planar or non-planar. So it should work for non-planar cases.
Other questions? You take that down.
Okay, so just a quick one. So the point is that given a set of ansatz, you have too few cuts conditions to solve it. And that's
Sure.
because on the cuts, these ansatz actually have linear dependency or non-linear dependency.
There's some redundancy is
Yeah.
also,
So,
yes.
but I mean, but Z and company has been doing multi-loop calculation in gravity and before. So did they not encounter this issue, or for some reason their ansatz size was smaller? You know.
Actually, I'm not quite familiar with that computation, but do you think that's related to some kind of supersymmetry structure inside that? Because this ansatz is designed for the general theory.
So that means that a supersymmetry
Yeah, you can see
shrinks your ansatz
yes,
size.
shrink for
and
very small
therefore-
set. Maybe you don't have this kind of redundancy, don't you remove that. But for QCD, you need that.
So it'll be worse for gravity.
I didn't do the gravity yet, but maybe that's easy, yes.
Other questions? Okay, if not, let's thank Zhang again. I think we take 5 minutes quick break before the goes talk.